right, people are still getting installed. Okay, welcome back from break, and it's my pleasure to introduce Tackyon Lee from Tackyon project. This is one of the most exciting parts when I'm going out and teaching intro courses on Spark. To me, this has been one of the most exciting parts of the stack, particularly for integration. And I've been very eagerly getting an update here about what's happening with Tackyon. And without further ado, I'll introduce. Thank you.
Thank you. So, hello everyone. So I'm Hao Yuan. You can also call me HY. So I'm going to present Tackyon reliable memory-centric storage system for big data analytics. And this is a joint work with Ali Gozi, Matei, and my co-advisors Scott and Young. So on the left side, that's the AMPLab. I'm a graduate student from there. And on the right side, that's the new Tackyon logo we just got last week. So, okay. So this is the outline of the talk. At the beginning, I'm going to give a very brief overview of the system and what's the problem we're trying to address, and then talk a little bit about research, and then talk about the open source status and the future roadmap. So let's start with the overview. Okay, first of all, memory is the king. So RAM throughput increases exponentially every year. On the other side, disk throughput increases slowly. So then this leads to the consequence that this memory locality is the key to achieve interactive response time. So this has been realized by many, like frameworks or the leverage memory to achieve better performance, like Spark, HANA, Cloudera, Impala. So then the question is the problem fully solved? The answer is no, otherwise I wouldn't talk here. So let's use Spark as an example here. We all know Spark here is a fast in-memory data processing framework, and it keeps one single memory copy of data inside the JVM and keeps track of the lineage which derive the data. Upon failure, it will use the lineage information to recompute the data. Say, for example, in this lineage graph, on the left upper side, the map got lost, data got lost. This is a machine failure. So it's simple just to recompute the data to get the data back. So this is how it works. So then, Spark is great. So many companies are using this and significantly increase the performance of the system. So there are still several issues. The first issue is how do you share the data among different jobs? Say you have a very complex data pipeline in your company, and there's one Spark job reads and writes data, and the other Spark job try to read the output of the last Spark job. So this case, on the left side, this one writes to they need to have an external storage to do this. On the left side, in this graph, it writes to the HDFS, and on the right side, it loads from HDFS. So this write process is slow. So this means that the whole pipeline will be slow. So the problem is even more complicated. Say, now you switch to Spark, but you still have some legacy code written in MapReduce, and then you want to put Spark application and MapReduce application in the same cluster. So how do you share the data efficiently and in a good performance between these different frameworks? So previously, it's still like, use HDFS is just slow in this case. So that's the first issue. Then let's talk about second issue. So in many of these kind of frameworks, like Spark, they share the process like between the execution engine and the storage engine. In this case, if you write a program or you have some experimental program, if the execution engine crashes, then the storage engine will also crash. So you will lose all the in-memory data. You will either recompute it or load it from under file system, which could be slow. And then that's the second one. So let's see what's the third issue. So say you have an input data and you want to two different Spark jobs to read the input data or some other data. So in a Spark, these different Spark jobs have to load their own copies into their own JVM. So this means that you have a in-memory duplication. And then also, because you have the duplication, also you have the data inside the JVM. So this will trigger a garbage collection issue, especially when you have a very large memory machine like 200 gigabytes memory per machine, or even more, think about several years later. So because of this, this motivate us to do this Tackyon project. We want to enable reliable data sharing at memory speed within and across cluster frameworks as well as jobs. So then we have one slide to talk about the solution. So what's our solution? The idea is simple. So we push the lineage concept, which has been successfully applied at the framework layer into the storage layer. And then, in the meantime, we want to use the memory aggressively. So in this case, we have two facts. The first one is we only have one data copy in memory, no matter it's read or write. But for performance, you may want to have multiple copies for read if you have hotspot. And the other fact is, so the system also relies on the recomputation for the fault tolerance. So this is where Tackyon sits in the stack. So it sits between computation frameworks and existing storage systems like HDFS, S3, GlassDFS. So Tackyon sits in the middle. And then this is the architecture of the system. It has a very simple architecture. It has a single logical master, keeps tracking the location of every file, what's the state of the cluster. And then it has on every single worker node, it will run a Tackyon worker daemon to manage the local space. And then besides the worker daemon, we also have a RAM disk to store the real in-memory data. And if your application has a data locality, it will access the RAM disk directly without going through any other process. This will guarantee the memory performance. Also from the graph, you can see that even though we have a single logical master, we have standby masters. And we use Zookeeper to have a master fault tolerance. That's the architecture of the system. So from this architecture, you can see that if the data is in memory, for read, you will have a memory throughput. So what about write? So we have this lineage concept. So the concept is the relationship among files. Say, for example, you have a file A, you have a file set A, which is group file, and your Spark program reads A and generates B, another set of files. And then your file set C, you have a Spark job to read C and generate D. So after these two jobs, you have a MapReduce to read B and D to write E, this E. So this whole information about the relationship among these files, how to regenerate this data, is called lineage. So Tackyon keeps this information. And then when an application writes to the system, it only writes a single in-memory copy. And later on, if the data got lost, Tackyon will be able to recompute this lost data. That's the idea behind the system. So then, after this brief introduction, let's revisit all those issues. So now, how to share the data between different frameworks or jobs. So you have this Tackyon in the middle. So you just write into the system at memory speed and also load at memory speed. That's the first issue. And the second one, because we have this Tackyon in the middle, so if your execution engine crashes, your data is still in Tackyon's memory, so it's fine. So it's okay. So for the third one, also you put most of the data in Tackyon. So in this case, two Spark applications, they will be lightweighted, right? So there's very minor data in memory in the JVM. So the GCU issue will be significantly improved. Okay. So after brief overview about the motivation and the problem we are trying to address, let's talk a little bit about research. And I want to point out here is for the research thing, it's not fully in our open source release yet, but we are working to make it stable and to be in the open source release. So okay, so we said we want to rely on the lineage information to do the recomputation to get the missing data back. But in this case, you have a machine failure. Someone knocked down the machine. So then that server contains some data you computed last month. How do you guarantee the data will come back quickly? So in our research, this lineage concept enabled the asynchronous checkpointing, which means that when the application writes the data into the memory, it's still at the memory speed. And then in the background, Tackyon will be able to asynchronously flush the data into the underlayer file system, which could be HDFS or S3. So then we have an algorithm called edge algorithm to decide the order to do the checkpointing. Say, for example, from a high level, it is we want to check from the lineage graph point of view, we want to check on the leaves first, and in the meantime, we want to check on the hot files with a high priority. And then, based on this algorithm, we can have a theoretical bound on how much cost we need to recompute any missing data to guarantee we have a reasonable SLA on any data. So that's the first issue. For the more detail, you can read our paper offline, and you can also talk with me later. For the second issue is, say we do the recomputation, right? To recompute any data if necessary. So how do you allocate the resource for the recomputation? Say, what if you have a high priority job in the cluster and you don't want to slow that job down? So in this case, we worked on our recomputation resource allocation strategies for two common schedulers in the cluster resource manager. The one is priority-based scheduler. The other one is fair sharing-based scheduler. So for the first one, basically we do you have some normal jobs, J1, 2, 3, with different priorities. And then you came up a recomputation job called R2, which recompute some data needed by job 2. So in this case, so we launch this recomputation job with the lowest priority, but if J2 requires the data computed by R2, so R2 will inherit the priority from J2. So the story also goes on. If J3 also requires the same data with a higher priority, so our job's priority will be increased. That's the priority-based scheduler. Then for the fair sharing, we have a similar story, but it's a little bit more complicated showing here. So you have different jobs, 1, 2, 3. They have different shares, W1, 2, 3. And for all the recomputation, they share the same share, which is 1, the minimum share unit in the cluster. So whenever you have any field data, you will put recomputation job for those data under this share. So it guarantees that if there's no other job in the cluster, this will still get a full resource in the cluster, but there are other jobs running with a bigger share, so those jobs will definitely get much more resource from the cluster. So then the problem is sometime later, say J2 also requires the data computed by R2. In this case, you see that the partial resource used by J2 will be reallocated to recomputation job R2, and the same story applies to the job J3 also require the same data later, and will share the resource with R2. And after the data has been computed, all the resource will get back to the original jobs. So that's the two scheduler strategies for two schedulers. Okay. So then let's talk a little bit about the performance we've seen. So this is a comparison with the in-memory HDFS. We deploy the HDFS in the in-memory cluster. So, but it still needs a replication to do the fault tolerance. In this case, for the write throughput, so Tackyon has the memory throughput right. It can achieve like 450 gigabytes per second for a cluster with 30 nodes. It's the EC2 cluster with 10 gigabits Ethernet. So for in-memory HDFS, it's quite far behind for the write throughput. And then we did a theoretical computation for the maximum throughput you can get for a replication-based file system. So we assume 2 copies and 10 gigabits Ethernet. So you can see the difference still quite large. That's the green line in the graph. That's the first graph we want to show. The second one is we want to see how much performance gain we can help on the Spark side. So this is one simple Spark job, which is grep. So we run this Spark job in 3 different settings. The first one is we cache the data in the green line. We cache the data in Spark, and in the deserialized mode, and then do the count and do the grep. The second one is it's a green line. We do the Spark cache in the serialized mode, and then we do the grep. And the last one is we just keep the input data in Tackyon. We call it TFS here. So the upper graph is the overall result for a single machine. To examine this carefully, we just use a single machine with 240 gigabytes memory. So as you can see, and on the x-axis, that's the gigabytes, the raw data size in gigabytes from 0 to 180. And the y-axis is the execution time from 0 to 300 seconds for this case. And the bottom graph is the enlarged area of the left side of the upper graph. As you can see that at the beginning, we have a smaller size data. So Spark cache mode is faster than the by loading data from Tackyon. For the deserialized mode, it has no overhead of deserialization. For the Spark cache serialized mode, still it has no overhead of loading the data from outside the process. But when you increase the data size, say for example, when you reach around 40 gigabytes raw data, for the deserialized mode, you couldn't handle more than that. The reason is simple. Because you use the Java object has a much higher overhead memory footprint to keep the data inside the JVM. So you couldn't do more than 40 gigabytes in this case. Then for the Spark cache serialized mode, you can do much more. But still, when you reach 90 gigabytes, you have a serious trouble. One thing is GC issue. The other thing is how to grab the data, how to grab the space from the OS. Let the OS give you the space rather from other process in the operating system. This is also hard. So you can see that from around 80 gigabytes, Tackyon will definitely bring you a lot of benefits here. This is the performance for a single job. So for multiple jobs, you will see better, even better performance. So then after this, we just want to show that for Tackyon, since we provide master fault tolerance, we can recover the master failure quickly. In this case, after realizing the machine is down, the system can recover like within 1 second for several million files in this test. Okay, one more interesting issue we want to talk about here is, Tackyon relies on the recomputation to do this to achieve fault tolerance. So one natural question is how much resource the cluster will be used by the recomputation. So in this, this is a theoretical analysis on the worst case, and we use the trace from Facebook and Bing. And for the cluster size, we use from 1,000 nodes cluster to 5,000 nodes cluster. And on the x-axis, that's the memory size per machine from 128 gigabytes to 1 terabyte per machine. So from the analysis, we got the conclusion that in both traces with 5,000 nodes cluster, the recomputation will not use more than 1.6% of the whole cluster resource. So this is comparing with the average utilization of this cluster, which is around 30%. So 1.6 is pretty small. All right, so then let's talk a little bit about our open source status. So we open sourced under Apache 2.0 license, and we released 0.41 early this year. Just to prove this is true, this is real, we have a snapshot on the GitHub, and we have more than 800 stars here. And then more than 15 companies, they already contribute the code base. And there are several companies that put full-time employee on this. And Spark and MapReduce applications that run on top of this without any code change. So as I said, now you develop new applications in Spark, but your legacy MapReduce code can still run in the same place. So then let's show a little bit more detail about our release growth. Last year, April, we had our 0.2 open source release with 3 contributors. And then we had 15 contributors later last year in 0.3. And in 0.4, we had 30 contributors. And next month, we'll have 0.5 release. And we haven't counted the number of contributors yet, but it should be more. So, okay. The other cool thing is most of these contributors actually come from outside of Berkeley. And we counted it's more than 75% of the contributors, they are from outside. And the other news is from Spark 1.0, so Tackyon is the default off-heap storage solution for Spark. Basically, you can say spark.persist off-heap, then the data will be stored, the RDD will be stored in Tackyon. So we'll have one slide to show how to use it later. And then, thanks to the Red Hat, so Tackyon is also in Fedora distribution. So if your machine is connected to the Fedora channel, you can use one command to install this on your machine. Also, early this year, the company called Artigio, they commercially started to support Tackyon commercially. And also, earlier, several days ago, so there is a blog post from Databricks. So H2O did a integration with Spark, and they share the data through Tackyon. And this is a snapshot of the blog post. Okay. The other thing is I want to show is how to use Tackyon. So this is a Spark MapReduce Shark job without Tackyon. So you can see that from Spark, you say file, this is RDD, equals to Spark contest, and then load the file from HDFS. This is how you use without Tackyon. And then you have MapReduce and Shark. And then with Tackyon, you simply change the URI from HDFS to Tackyon. As you can see, this should be not hard. Yeah. Thank you. So, and then, as I said, so from Spark 1.0, your application should be able to store the data, your RDD off the heap in Tackyon with a simple API. The first line is what we have shown. You can load the input data is loaded in Tackyon's memory, and Spark just load the data from Tackyon through the RDD interface. And the second line, you will see that this RDD, you can say .persist, and then it's off heap. That will put the data in Tackyon. And this is our initial integration, and we'll make this integration more efficient. And we'll try to try to share the same RDD across different Spark jobs like pretty soon. Also, I want to thanks to our code contributors. There are more than 40 contributors now, and from the following companies like Yahoo, Intel, like Nokia, these companies. And okay, so then let's talk a little bit about the future. The first thing is, what's the goal? What's the goal of the system? So because we got this question a lot. So the goal is pretty simple. So we just want to better assist components in the stack to achieve the better performance or easiness to use. Say on one side, we deeply integrate with a Spark, and MapReduce can also run on top of this. Shark also has a close integration. And as I said, H2O, their framework can also load the data from Tackyon. And also, all these other frameworks, we're also very happy to work with them to have the integration. On the other side, for the deeper storage, for the underlayer storage in Tackyon, we also work with different storage system. Obviously, the first one is HDFS, and we want to support it well. And then we can also support S3, which means that you have an S3 cluster, and you have an AWS cluster, and you have S3 storage. And then by deploying Tackyon, you can easily load your open access data into the Tackyon's memory, and then without access S3 anymore. But you're right, we'll go to S3 later. And then besides S3, you can also work with local file system. You can also work with Cluster.fs. This is also a contribution from Red Hat, and also we'll have better support even for NFS and also for Ceph. So of course here, I want to say that we are very welcome any collaboration. So please come to me after the talk if you have interest. And then this is a very, very short-term roadmap. So this is just a short list on a subset of what we are working now. Say, for example, for the Ceph, we want to have the Ceph integration. So this is the effort led by Red Hat, and we want to have the hierarchical local storage. This is led by Intel. So for the hierarchical local storage, it's not to get rid of the local file system, just to manage the local storage better. But you still have the underlayer file system, like HDFS S3. And then we want to further improve the Shark performance, and this is an effort by Yahoo. And we want to better support multi-tenancy. This is an effort led by MPLAB. So there are many more other things we are building from the lab, and also other many industry collaborators. And of course, if you have some requirements, so please feel free to come to me after the talk. Then this is a summary of the Tackyon. So Tackyon is a high throughput, fault tolerant. It's a memory-centric storage system with lineage as a first-class citizen. And it further improves the performance for like frameworks like Spark, you know. And then it has a healthy community with more than 15 companies like contributing within a year. That's all. So if you want more information, you can visit our website and also our GitHub, or just feel free to email me. Thank you. Sure. Thank you. Yeah. What's the question? Oh, the question is, can you use Tackyon to eliminate shuffle disk I/O? I believe for now, no, but that's definitely on the roadmap. Yeah, thank you.
Are you planning to, in Tackyon, are you planning to use kind of tiering and memory storage? For instance, strict RAM, lazy RAM, RAM to SSD, while for losers, the RAM.
Yeah, so the question is, you have different storage media, and what do you use, and whether you can use it together, right? So for the first question, if you have different storage media, you can just use it now. It's not necessary to be like just normal memory, right? It could be anything. So for the theoretical local storage, as I said, Intel is working on this feature, and I think will be released pretty soon. Maybe. I'm sorry.
In HDFS 3, I've had along with compression, with encryption on disk encryption.
Encryption.
This the tiered storage, SSD separation, SSD versus RAM,
Uh-huh.
and disk, the disk chunks, and encryption. That's too big contribution.
Oh yeah. So basically, in this case, you can have like RAM, SSD, disk. It's okay. Yeah. So well.
It's not handled by Tackyon. It is not handled by Tackyon.
Oh.
You're not planning.
So if the feature is ready, Tackyon can handle it, but it's not going to replace HDFS or S3. It's just manage the local storage, but not the deep storage like HDFS S3, you know? Yeah.
I'm just trying to say, okay, you're storing blocks in Tackyon memory, yes? You can say these blocks can be moved out on the disk. It's a lazy storage, yeah? These blocks can be moved out on the SSD disk. This block will be lost if it's necessary on the disk drive. You see my point?
I see.
I'm talking about the Tackyon part, the roadmap on the Tackyon
side. I'm saying when the feature is right, when that feature is ready, what you said can be done in Tackyon, can be handled by Tackyon. That's what I said. But we can talk offline. Thank you. Yeah. Yep.
Way of characterizing the applications that can run on top of asynchronous checkpointing, because not all applications can go through.
That's right. So that feature is not in our. So basically, we are working on the close integration, but what you said is not there yet. But of course, obviously, it's not everything. So, but most applications which can run on top of MapReduce or Spark should be able to use this. Yeah. Okay. Oh, the question is, how do you handle if the file is too big for memory? So the way is so Tackyon has two ways to do this. One thing is we have a pin operation. Basically, you can pin the data in memory. The other way is we just do LRU. So for the data you cannot fit in memory, they stay in the under file system. And we are working on a generic interface to allow plugging different policies. You can plug in LFU, whatever, you know.
Just like the Spark cache, right?
That's right. Thank you.
So you had some really impressive benchmarks for Tackyon, and I was wondering, are there any reasons why you shouldn't use it? Like, is there a break point where it's small enough that it doesn't make sense?
So the question is when you should not use Tackyon. Okay. So this is a great question. So so I think from the software itself, we are building more features. There are certainly something you couldn't do it now, right? So for example, as I said, we are doing this hierarchical storage. Maybe your data couldn't fit in memory at all. So in that case, maybe there's very little benefit in using it. But this will, in order to use it, you need to deploy another layer in your cluster, right? This is the overhead. But along the way, when you build more features, you have more motivation and benefit in deploying it. And also, along the way, since there are several companies that are already using this system, and when this process goes on, when more companies are using this, the product itself, the software itself, will be getting more mature. From that perspective, it's better for you guys to start to do this. But we also welcome anyone to use it right now. Yeah, thank you. Yep.
So, do you actually segment those blocks, create blocks for the client, and then store it in multi-node? And what if one node
So,
crash, how long will it take to recover? The last node.
I'm sorry? Oh. So you are saying if it's a single node failure, how long it takes to recover, right? So in the current release, the way you recover, you just load from under a file system. It's just the speed to load from there. And then for the feature, for the research agenda, we said that will take from our experiment, it's less than 30 seconds. Yeah, around 30 seconds a minute. That's that level. Yeah.
So we are talking about probably lineage coming from different paths.
Yes, that's right. Yeah.
And that still takes 30.
Yeah, 30 seconds, 1 minute, yeah. 10 seconds, depends on the workload, or how heavy or light your workload is. If your workload is light or bursty, you don't have much data not in memory, not in under file system, but just you did asynchronously, doesn't affect your performance. But for the recovery, it should be very fast. Yeah.
If we have other questions, we can move them out into the hallway maybe?
Sure. I'll be in the back, so outside the door. So feel free to come to me if you have questions. Thank you. Yeah.
Wait, are you on your laptop? Looks good. Alrighty, next up, Frank Nothaf from AmpLab, talking about Atom. Looking forward to it.
Hello, I'm Frank Notaft. I'm a grad student in the AMP Lab. This work is Atom, which is a pipeline system for doing scalable genomic analysis on top of Apache Spark. This is joint work between me and many other people. So Atom is a joint collaboration between Berkeley and about 5 or 6 other institutions, with the main contributors being at the Genome Bridge in Boston, Massachusetts, and Mount Sinai Hospital in New York City. So as you all saw Dave's talk earlier today, genomics is a really big data processing problem. Yeah, if you start looking at it, whole genome files are huge. You have a single sample is about 250 gigabytes to process. You have 4 samples that already puts you over a terabyte of data. Then biological systems are complex. There's a lot of imperfections in the way that we collect and process data already. Dave was showing you the picture. We have these spools. We cut up the spools, we get the words. Unfortunately, when we do this with a real genome, we don't get all the correct words. We have about a 2% error rate, and we're looking for these 1 in 1,000 variants. So we actually have 50 times more errors than actual variants that we see. 200 times, not 50 times. Additionally, when we want to do this analysis, part of the way that we overcome these errors is that we look at many genomes at a single time. Part of this is just to overcome issues where the sequencer sequences the data incorrectly, or where there are certain biases in the sequencing. But as Dave showed you earlier, when we looked at that example with where we have all the patients who have schizophrenia, and we're trying to understand if there's a genomic driver for their disease, we couldn't make heads or tails of the data until we got to about 50,000 patients. The way they used to do this was with what they call a SNP chip, which produced a lot less data. Right now, we want to use whole genome sequencing because it gives us a lot better resolution. We have much more data that we can interpret. The only problem is now, if I have 50,000 patients at 250 gigabytes a pop, I'm looking at several petabytes of data. Then, finally, we always get back to that, as Dave was showing with the example of the child who had the brain disease. Analysis time is definitely a matter of life or death. Right now, if you have a 250 gigabyte file, which is the minimum size file that you need to be, to do clinically certified genomics, it takes over a week to process your genome. So that's not necessarily compatible with saying, somebody comes into the lab, they've got a life-threatening illness, we'll get to it in the next week. So we're really hoping to, 1, make it so we can do a scalable analysis, and 2, to use the ability to scale up so that we can really drop the latency on a single experiment. Just kind of to refresh your memory, as I was saying, our files are about 250 gigabytes that we operate on. We're trying to find these 1 in 1,000 variants. Once we have operated on and processed the data, we're down to about 10 to 100 megabytes of data that summarizes how a human is different from the reference genome. And Dave took you through this example, but what we're trying to do is, we have a single human genome. We essentially read it by sampling. We shred up the text into these short chunks. Unfortunately, we can't read a single chromosome straight. And then we have to find a way to reconstruct this text. And ultimately, this is an inference problem. There are several different strategies that we use. Some of this is essentially trying to calculate what abundance of reads you have that is in favor of a certain allele at a single position. Alternatively, there are some graphical modes that people use to essentially find contiguous segments and assemble a graph from that. So this is something that we're looking forward to hopefully building in GraphX soon. For Atom itself, so Atom is a set of 3 things: file formats, API, and a command line interface for doing genomic analysis. As Dave was explaining in the talk earlier, we have this big pipeline that we have to run through, and we spend a lot of time moving data through pre-processing stages. So these pre-processing stages handle a lot of the, just cleaning up the data, it's the typical problem in any big data pipeline. You get data, it comes in, it's dirty, and you have to make some process to clean it up before you can run any sort of analysis. A big problem that we face in these current pipelines is the way that the pipelines are structured is we're doing one pipeline stage, we read in the data, we spill the data, we do all the processing, we spill it to disk. We run another processing stage, we read it in, spill it to disk. This may sound like a familiar pattern that we've tried to get away from in the big data sphere. So this is a great fit for Spark. We're really looking at a true iterative pipeline. We can gain a lot from leaving things in memory. However, there's a few other things that we can benefit from. What we've implemented right now on the file system side or on the file format side is a schema-based description of genomic data. Right now, people have, genomicists are kind of laughed at in the science community because the number one thing we like to do is invent new file formats. Because every few years we find, that handcrafted, handwritten file format we had a few years ago, just not the state of the art anymore. So we're saying, instead of having a handwritten file format, we describe things with schemas. We can easily move, what our back-end file store is as technology evolves. We then built this API on top of our file formats, and then this command line interface implements all of the current processing stages that people are using just by calling out to the API. So, really just the design goals that we have is that, as I said, we want to be able to be scalable so that we can either handle more data or handle the same amount of data quicker. And then we also want to be able to efficiently parallelize the systems. As I was saying, one of the reasons that we actually moved away from the conventional file formats isn't just that they're kind of hacky and hard to work with. They do a lot of bit twiddling and so on to improve compression and space on disk. But one of the big things that they sacrifice is the ability to do reads and writes in parallel. There are several systems that implement Hadoop readers and writers for the current file format, which is called BAM. But right now, they're really limited to speed up on 16 machines. That's what for us, to hit, like we have this big goal of hitting, the ability to process a single genome in an hour instead of a week. And part of the way we're doing this is we're throwing a lot of machines at the problem. So if we're limited to a speed up of 16 on read just because of our file format, that's no good. And additionally, to query this file format using something like SQL, you have to write a lot of essentially just really, really not pretty conduits. So there are people whose entire PhD thesis has been writing a SQL adapter to the current file format. So our goal is really just to take the current kind of ad hoc, handcrafted state of genomics and to try to move things so that it plugs in nicely with ecosystems so that it can easily be used from whatever the current state of the art is on the computing side. From a project perspective, we've been going at this for a little bit over a year. The first work started in April of last year, and things really picked up in September. So we're about 25,000 lines of Scala code. We have a little bit of Java sprinkled in as well. Everything that we do is Apache licensed. And right now we represent about 18 contributors from 6 institutions. A big milestone that we're pushing for is to actually have a production quality release. We're shooting for a production quality release towards the end of this year. What I'm going to talk about a bit today is both how we, some of the optimizations that we've made down at the file block level and some of the processing that we're doing in memory, some of the pipeline transformations that we've done. So, our system is built, at a low level, we assume that we're underlied by some sort of a block store or some sort of a distributed file system. Nominally, we use HDFS, but we've done a lot of work recently to optimize for using Amazon S3. kind of once we kick up a level, as I said, we're schema oriented. We store everything in Apache Avro. Part of the reason for this is, bioinformatics is definitely not settled on a language. We're not homogeneous at all. Apache Avro has very solid support across about seven different languages. So it makes it easy for us to interact with other applications that are out there. Finally, obviously we're running on top of Spark. That's why we're here at Spark Summit. But some of the Spark is right now the big workhorse in the pipeline. It allows us to churn through a lot of data. What we're really excited about, and especially as we get close to our production quality release, we're going to be looking at a lot of these downstream analysis that will be built on top of Spark, or on top of Shark, on top of GraphX, on top of MLlib. We've actually recently rolled out a prototype of what we call a beacon using Spark, or using Shark. And what this allows you to say is, I'm interested in seeing if this collection of files that you have has this single allele of a gene. So you can submit a query to it, and then we return a really quick answer as to whether we saw it in whatever the sequencing experiment that you're interested in is. So for our underlying storage format, we're actually writing data out to disk on Parquet. Some of you may be familiar with Parquet. If you're not, this is a open source columnar file format that was created by software engineers at Twitter and Cloudera. This was originally based on Google Dremel, and it just was recently accepted to the Apache incubator. So it's an exciting project, and it's growing really well. There were several big reasons that we chose a columnar file format. One, with a columnar file format, it's very easy to select specific columns, and this actually really lines up very well with genomics. There's one specific translation that we were looking at that people do a lot to check the quality of the sequences they have, essentially to make sure, the sequencer, did it spit out good data, or did I mess up my chemistry when I was running my sequencing experiment? It essentially looks at, we have about 33 fields in our schema. It looks at 6 of them, and specifically 2 of the fields account for 70% of the data on disk. They just don't compress well. They're very large fields. And of the 6 fields that it reads, those 2 are not present. So just by having a columnar storage format that allowed us to actually specify what columns we want to read instead of reading the whole records, we were able to get about a factor of 20 speed up right there. And this is even an optimization that they made in the legacy file format, is that they do lazy decoding. So even then we weren't really paying a full penalty for that, but we were still sucking the bytes off of disk. So that was a big benefit. Additionally, so Parquet actually has several different compression formats. Being a columnar store, it's really is awesome at compression. So one, we're able to actually fully denormalize our schema. So the previous schema had this large header that was part of the thing that limited its parallelization. The header always had to be broadcast out when you read it previously. We were able to fully denormalize the header. We got rid of it. All of our files are headerless, which is wonderful. If you want to access the header information for your, for a single record, it's all contained right there in the record. And even still, we're about 5 to 25% smaller without having to do any manual optimizations and with a fully denormalized schema. So as I was saying, we get really fast scans because we have the columnar, we have the ability to select specific columns. And another thing that's really great is that it also gives us these projection, these push-down predicates. So one of the common access patterns in genetics is, surprisingly enough, to say, I want to read a specific region of the genome. So for example, there are several companies out there that are looking at doing analysis of cancer risk, for example. And in one of those cases, you might say, oh, what's a gene that's commonly associated with cancer risk? Maybe it is, I think a lot of people have seen, the New York Times. There have been articles, about celebrities who have, one of the BRCA 1 or 2 mutations. So what you might say is, well, we did this sequencing, but what we really want to see is, does this person have a mutation in their BRCA 1 or 2 gene? So you would say, I have this specific range, it's maybe, order of 10,000 bases out of this, 3 gigabase, this 3 billion bases genome that I want to read. So in Parquet, what we do is we say, okay, you're only going to deserialize those fields. So you're going to look at what chromosome we're on and what the start and end positions are. And then we're going to see if that passes our, predicate. So once again, these are 3 small fields. They're, we did some looking at this, and it's about 2% of the size of the data on disk. So we read that. We read that for all of the samples, or for all of the records. We only select then the records that that pass the predicate, and we actually fully deserialize those records off disk. So that gives us somewhere between a 3 to 10x improvement on performance, depending on how much data we are pulling off disk. How many data or how many records are failing the predicate. Finally, there are a few optimizations that we're working on. The team that we work with at the Genome Bridge in Boston, their main goal is to support a group of population geneticists who have these big data sets that are sitting on S3. So one of the big things they've been working on is a way to essentially make Parquet act natively as if it's running on HDFS while it's going out to S3. So there's a few optimizations they've been working on recently. They're currently sitting in the Atom repository, but we're working on separating this out from the main Atom repository and into a different repository, because this would be useful to more people than just the people who want to analyze genomic data. Additionally, we're interested. A lot of people like to use Amazon's spot instances because it saves money. So one of the things with this is that you might want to modulate the amount of work that you're running as the price of spot instances changes throughout the day. So this is something that we're looking at, if there's a smarter way to essentially schedule work for these long-running task flows. Finally, I'll talk about a part of the algorithmic work that we're doing in our toolkit. As we were mentioning, there's a lot of these stages of these pre-processing where we're trying to clean up the dirty data that we get out of the sequencing. And one of these stages is BQSR, or for most of everyone else, base quality score recalibration. So we mentioned earlier that DNA sequencers read 2% of the sequence incorrectly. And what's good, though, is that for every single base that they read, they provide us a quality score, which is essentially just some measurement of how likely they were to have read that single base correctly. So this is good, but one of the problems is that a lot of the errors that we have in the reads are actually, there are these systemic errors that, there are these correlated errors, and the sequencer, when it's assigning a quality score, can't take that information into account. So for example, when we do the sequencing, what essentially happens is that base by base, we read off all the DNA from all of the reads in lockstep. So one of the frequent places where a correlated error happens is that all of the bases that we read in cycle 50 are incorrect. It just happens that something was strange. Maybe the sequencer overheated and we just didn't read the values correctly that round. Who knows? However, when the sequencer is trying to make these local scores, it can't score correctly. So the way that we handle this is we actually split. We essentially take all of the bases together and we try to create some sort of a tree that we aggregate data on. So what we like to think of is that all of the data has these covariates. So one of them might be the read groups, and what that essentially means is that all of these reads came from the same part of the sequencer. So they were all sequenced together. They share common chemical properties. Then below that, what we have here, the second row down might be reads that or bases that all had the same quality score. From here, once we've divided all the bases up, what we try to do is we try to mask them and then count how many of the bases in this bucket were actually incorrect. So we mentioned earlier, there's a lot of, there is about 1 in every 1,000 bases are variance. The way that we count whether something is correct or incorrect is we expect that it's going to match the reference unless, so like we expect that something is always going to match the reference, and that is our definition of correct. So we align the reads to the reference genome. We say, is this base, does it match the reference? If it doesn't match the reference, we count it as an error. However, this is kind of crude because, as we said, 1 in every 1,000 bases should vary from the reference. What we actually do is we keep around a table of all of the variants that are known to happen, with a reasonable likelihood, reasonable rate of occurrence in humans. And this table is about, it's about 3 gigabytes, and it's, the way that we say is a reasonable rate of occurrence is that it occurs in 1% of all humans. So we mask out all sites where we expect change to happen, and then we just go through, we put things back into this bucket, into this tree, and in every single bucket, we evaluate how many of the bases were correct, how many of the bases match the reference, how many of the bases were incorrect, and we recompute the quality score that we expect to see. So, as you can see in this table, for example, we would say, maybe for this quality score of 16, we saw 105 samples that had, that fell into this covariate, fell into this bucket. One of them was incorrect. We had said it should have been a quality score of 17, but this would lead us to revise our estimate down a little bit to 16. And in case these numbers aren't exactly, 16, 17, don't really give you great context, this is a negative log, it's a log likelihood of failure. So quality score of 10 is 0.9, 90% chance of correct. Quality score of 20 is 2 nines, 30 is 3 nines, and so on. So that's just a brief overview of what we're working on and some of the strategies that we're using to accelerate our pipeline. As for the future, what are we doing? Our real big emphasis right now is pushing towards the production release, and the way that we're trying to hit this production release is to make sure that we're as close as possible to the current best of breed algorithmic tools out there. So we're really comparing very hard on accuracy. For those of you who aren't familiar with bioinformatics, what's interesting, Dave showed us earlier, we're hitting about a 50x performance improvement over the current state of the art. And one thing he didn't mention is that we're actually doing this at a lower cost. While 50% improvement at lower cost is good, the fact of the matter is biologists are not they're not interested in those trade-offs if we sacrifice any accuracy. So we're really pushing hard on this, and what's actually been very, very good and very fulfilling is that we've, when we've been pushing hard on this accuracy, we've actually found bugs in other tools. So in the BQSR example, this base quality score recalibration, we were trying to compare to the only other tool that implements this, that's used in a lot of clinical sequencing centers. We were off in 5,000 paces, and we wound up finding out that the reason that our results didn't match the current best tool is it was actually a bug in the old best tool. So it's a good feeling, but it's hard work. So we're pushing towards that for the end of the year. There's also been a lot of interest in the community in language bindings for other languages. So we're hoping to sometime towards the late summer release Python bindings for our API, and maybe eventually R bindings as well. And finally, we're highly involved in this project called the Global Alliance for Genomic Health. So they're building an API that's supposed to be vendor neutral for accessing genomic data. So we're really interested in this in the spirit of pushing along open science and reproducible science. So we're building a set of tools for launching up a cluster and administrating a cluster running Atom. And one of the emphasis there will actually be fully supporting this API from the Global Alliance for Genomic Health. And finally, we're an open source project. We love to have contributions. We do maintain on our GitHub a list of open enhancements, and we tag. So the nature of our project being kind of at the cross of disciplines between computer science and genomics is that some of our open issues require more computer science knowledge. Some of them require more genomic knowledge. We've tried to tag all the issues that don't require genomics background as pick me up. So if you're interested in taking on an issue, feel free to look there, comment. And as I don't have the nice big picture of Matt as Dave did, but we are also looking for 2 full-time engineers. So if you're interested in the position, you'd like to join us, please find Matt somewhere. I'm sure he'd be interested in talking to you. And finally, I just want to acknowledge all of the collaborators that I have on this project. We're really lucky. We have a huge team collaborating across many different sites. Every month we have a few new people who pile on to the project. Thank you all for your time, and I'll take some questions. I got them all in the talk. All right, that's good. No. Yeah. Yes, one question, please.
Once you've processed your genome to retain only the variants for that particular sample, do you have an easy way to go back and say you publish that variants for other researchers? Is there a possibility to go back and say, oh, I found some issues with the genes? Is there some way to see, to verify the rate that led to that?
Sure. So that's a good question. Essentially the question was, yeah. So the question was, let's say I've done my processing and I've arrived at a set of variants. Is there a good way to publish the variants so that if I wanted to, essentially go back and debug them later, someone comes and says, hey, I'm not sure if this was the correct call, or I want to experiment on this further. Is there a good way to publish that? Yeah, so one of the things that we've been working on, actually in a slightly downstream project that does the final analysis to take the post-process reads and to compute variance, is to emit the essentially the sufficient statistics for every stage of analysis that we do. So the final stage of processing is really just a statistical inference problem. And in that, we collect a lot of statistics, and we emit a lot of those statistics with the variance, but we're also looking for ways to capture some of the more region-specific information that's not currently emitted with the variance, and to serialize that to disk so that you can go back and, one of the use cases is debugging it later, but another big use case is using that as a prior for the next time you call a sample.
Just had one question.
Yes.
The traditional policies used for swapping out of memory and this do not work for genome data. So do you have any specific ways of handling that, or how are you doing that?
Yeah, so the question was that traditional policies for swapping out of memory onto disk may not work for genomics, and whether we have any specific policies for that right now. That's not something that we've really been looking at very seriously. We've been operating on nominally on clusters that are much larger than the input data size for the purpose of testing the latency of our system. It is a very good question. It is definitely something that we're going to have to look at more seriously sometime soon, especially as we start considering the cases where we're processing many samples at a single time. Right. Thank you all for your questions.
Oh, they try. Exactly. No, I'm on TV. What's that? Yeah, then we're filming. Okay, what's going on here? Hi, it's actually not accepting input. The laptop's not accepting input. Do you want to use that instead? We might, for whatever reason, this one is keyboards. Well, this whole I don't know why the other one isn't accepting input keyboard.
2 seconds, I gotta change your display options.
Great. Okay, I need this one down lower. Great. Next up, I'd like to introduce Peilong Li with Sparkling and
Thank you for Paco's instruction. It has been a great experience learning and researching Spark during the last half year. I found there are many advantages of Spark over other cluster computing systems. However, I also find there are some points that Spark need to be improved. Dear ladies and gentlemen, today I'm going to talk about our Sparkling project, identification of task skew and speculative partition of data for Spark applications. This is a joint work by 2 universities. My name is Peilong Li. I come from UMass Lowell. And we also have Xiaobing and Dr. Tian Zhao from University of Wisconsin-Milwaukee, and also Dr. Yan Luo and Dr. Yu Cao from UMass Lowell. Okay. We all know that Spark has provided web UI and other instrumentation tools such as Ganglia for users to better understand the performance of their application. However, the more I use those tools, the more I found why it's not providing the information about why an application does not yield expected performance. Instead, our Sparkling Web tool provides better execution. Oops. And, sorry. Oops. It happens. Okay. Sparkling Web Tool provides better execution visualization, as you can see in the later slides. and also it provides an in-depth statistical analysis. I also find Spark may generate unbalanced tasks during doing the partitioning, which we call them data or computational skill. So in order to solve that problem, we have proposed two partitioning methods, one called decremented partitioning and the other called application-aware partitioning. So during the rest of the presentation, I'd like to divide the content into two parts. Part one, I want to talk about the sparkling web tool, and in the second part, I want to talk about how we mitigate data skew in our own Spark application. So first thing first, sparkling web tool enhances Spark application development in the following ways. First, it provides a more detailed metric system, and then it provides a task view and executor view to help understand the performance. And also, it provides overall performance with in-depth statistical analysis. And fourth, it had helped programmers to help avoid the data skew and also the small tasks. This is how sparkling web tool looks like. And if you are interested, you can check out our demo page for the Spark Summit. It is pr01.uml.edu. And if you click the very first button on the web tool, on the menu bar, you can go into the task timeline view. You will get an annotation bar showing the meaning of y-axis, which is task ID in this case, and the meaning of x-axis, which is time in seconds in this case. And also, it shows different colors with different meanings. For example, the blue bar stands for the deserialization stage in a task, and red bar stands for execution stage. And also at the last, you can see a total duration time showing the overall execution time for this current application. This timeline view shows the detailed information about how does an application performs on a task basis. From this view, we can easily see the transition between each RDD stages, and we can catch those tasks that has slowed down the whole application. And if you continue to click on the second button on the menu bar, you will go to the executor timeline view. In this view, we can also get a similar annotation bar showing the meaning of y-axis, which is executor ID in this case, and also the meaning of x-axis, which is time in second. And also, we can have some blue bars with numbers on it. That's the task ID. So basically, from this view, we can see the different tasks running on different executors. And we can easily see there are some short-living tasks like this, and also some very long-living tasks like these guys. And if you look into each horizontal line, which is the executor, you can also find there are some white spaces. That's the time during which the executor is idle, and that's the time we want to take full utilization of. Okay, if you go to the second button on the menu bar, you will get into the statistical analysis view. In this page, we can see there are in contrast with Spark Web UI, the table showing above provide an in-depth analysis on statistical properties of the application behavior. We can see we provide the maximum time and minimum time, average time, standard deviations on different stages, and also the scalar delay. And we also find that small tasks or empty tasks may introduce a high overhead to our Spark applications. So basically, we want to know how many percentage of small tasks exist in our application. So we provide this view to simply show the percentage of the small tasks. And also, we found histogram might be very useful for Spark developer to know the distribution of a target. So we provide 4 options for different stages, and also the scalar delay histogram. It's very interesting showing in this picture that we can see there's a high percent of tasks, almost 300 or something, showing the execution time of almost 0. And thus we call them the empty or small tasks. And we can also find there are some tasks that has execution time way much longer than the other, or the average tasks. That could introduce the task skew. Okay, in the second part, I'm going to talk about how to mitigate the data skew in our own Spark applications. We know that Spark has provided a speculative mechanism which can handle the stragglers, aka the slow node. But there are a lot of other applications like biomedical multimedia processing applications we use is it can generate a very high computational skew. I'm keeping talking about the computational skew or data skew, so where it comes from. Spark has provided the partitioning method which will divide the workload into slices with equal head count. But the problem is, what if there are unbalanced workload on each slice? And of course, that's we call the data skew comes from. And so to tackle with this issue, we propose 2 methods, partitioning method to mitigate data skew. What you can see here is a problematic partitioning. We know the next stage will only start from the end of this longest task. So basically, this period of time is wasted for your application. So the first way we do it, we call it decremented workload. We know that the start time of the longest task often determines whether there is any idle time between stages or not. So basically, we want the task that has been issued early have the heavier workload than the later ones. In that way, we will have less time being wasted. And the second way we do it is partitioning the RDD with domain knowledge. If with domain knowledge, we can make sure that each slice will contain almost similar computation complexity. So in this way, we will do the partitioning more wisely. You can see if we have the domain knowledge, we can know that this task might be the TAF might contain the TAF data. So we can partition the RDD into this way, which will have the stage execution time being shorted. So our test benchmark is the PRR benchmark. If you are interested, we have a paper publishing for PRR. You can check out the link, the reference below. And for a quick introduction to the PRR benchmark, we have image query and transmedia query applications, which contains SIFT and LDA algorithms, And the data set we use is Expedia articles, which contains 2,866 multimedia documents, including images and texts. And the domain knowledge we use for this case is edge pixel percentage, which is showing in the algorithm here. It equals to the number of edge pixels divided by the total number of pixels. Why we use this as a domain knowledge, you might ask. So first, it's very lightweighted, and also the image or image transmitter query application use local features. So edge pixel percentage is a very good stand for local feature complexity. That's why we use it. And in this slide, I'm showing the experiment result of using our own partitioning method. So on the very left vertical bars, you can see here is a Spark naive partitioning method, which has been normalized to 0 or to 1. And what you can see here is hand modified partitioning. The meaning for this hand modified partitioning is this partitioning is obtained by trial and error. So you can simply treat it as the ideal way of no data skew exists. So if without data skew, we can see the performance is lower, which has probably 23 or 28% reduction. And the second column here is by using the decremented partitioning method. And you can see here, it shows a slight improvement on this in this case. And if you're using the domain knowledge partitioning, you will get better performance. The best case is 11% of improvement. But you might see this improvement is too little, and you might want to ignore it. But in this case, we are using a very small Wikipedia data set. So if you want to try a larger data set, you probably have better performance, better than this. And I want to quickly go to the conclusion because my presentation is 15 minutes in total. And so the Sparkling Web tool provides more insight for developers on how to improve application performance by decreasing data skew and small tasks. And also our proposed automatic data skew mitigation algorithm shows a 11% increase of performance on our own biomedical benchmarks. So that's pretty much for today. And if you have any questions, I'm open for any questions. Yeah?
Yeah, for the decremented partitioning, how do you actually figure out which one is going to run longer without running it?
We will know which task could be issued earlier than others. So for the early task, we have a list of all the tasks with different workload. So for the early issued task, we want the heavier workload task being running on that task.
But how do you know which is heavier? So in your Wikipedia example, let's say I'm extracting n-grams, right? How do I know which partition of the Wikipedia dump is going to generate more n-grams than any one?
I understand your question. So you are saying how I know which task going to be heavier than others. We have do a profiling before running all the applications. So that's why we use edge pixel percentage as the domain knowledge. We run the profiling first, and we find which data might be tough data for our application. And we group that data into the heavier workload task group.
So maybe this is a dumb question, but would the profiling take up just as much time or more as simply running it with
Yeah, yeah. In our case, in our experiment, we have doing an extra stage, doing the profiling. So the profiling stage takes like 2% of the total execution time. So basically, you can overlook that part of overhead. Yeah, thank you. Yes, please.
Is there a way that we can use the existing or the visualizations that you were talking about on our existing stuff?
Oh yeah, we are working towards to open source this software if you are interested. But currently we are under beta development and we are not our alpha development, and it's not open for other developers to use. But we definitely want to make it open source, and I hope in this month we probably have it for others to use. Yeah. Yeah.
This is a deployment work. You have to deploy on every node, or for profiling, you have to deploy any plugin or anything on every node.
Yes, it's similar as the other algorithm you run on Spark. It's like you're doing an actual stage to do the profiling with domain knowledge you want to use.
Okay, so you basically submit your jar along with your job for profiling, or you have to install your plugin before you submit it?
Yes, that's the way we do it. Yes, please.
Based on your approach, is it possible your profiling result is different from what really happened? Assuming you have a 5 text, their profiling result might have a rank from 1 to 5. But when you really do wrong, maybe they got different order because of the profiling probably get a sample answer, right? So in that case, your method probably completely screw up, right?
I didn't really get your point.
How can you make sure the heavy text based on your profiling result will really happen when you really run the full set of the data?
Okay, so the domain knowledge really matters for this use case. If you have like stupidly choosing other domain knowledge like we previously do, and yeah, you can get like worse performance. Yes.
So you imply your sampling method when you're choosing the profile are very important for the whole thing.
Yeah, you have to very cautiously choosing your domain knowledge to do the profiling. Yeah. Thank you.
Sorry? Yes, just my.
Okay, so welcome to the last session of the day. So my name is Yang Rui. I'm from Databricks. So at Databricks, I spend most of my time on this machine learning sub-project of Spark called MLlib. Today, I'm going to talk about a new feature introduced in MLlib 1.0. It's sparse data support. But before that, since there is no general talk about MLlib during the first 2 days, but Amit is going to give an introductory talk about MLlib on the 3rd day, on Wednesday. So now everyone is going to the training day. So I want to give a brief introduction of MLlib. So MLlib is basically is a sub-project of Spark implementing many standard machine learning algorithms. The initial code contribution was from Berkeley AmpLab. It's the same group of people that created Spark. And it shipped with Spark since version 0.8. That was from September last year. And since then, we have received code contributions from 50 individual contributors. And if you check out my talk maybe a month ago, this number was 33 or 35. So it's really, we have more developers joining us. And I think the numbers will increase a lot after Spark Summit because there are many open PRs now. We're just waiting for review. So for machine learning algorithms, we cover just basic linear methods like logistic regression and linear support vector machine and naive Bayes. And we also cover decision tree for classification and also for regression. We implement alternating list squares if you went to the Spotify's talk today. And it's for collaborative filtering. And also we recently added an option that can allow non-negative constraints that give you the non-negative matrix factorization. So for clustering, we support k-means clustering. And for other decomposition or dimensionality reduction, we have the singular value decomposition and principal component analysis. So that's basically a standard coverage of machine learning algorithms. So in 1.0 was released in maybe in May, and we added many new features to MLlib. First, from users' perspective, we update the new user MLlib's guide, and it's more organized. And we add a lot of code examples for MLlib. So if you go to Spark documentation, you can see we support APIs in Java, Python, and Scala. And we have the code tabs, and you can click Java, and you only see code examples in Java. And then if you switch to Python, everything is just tailored for Python users. And in 1.0, we also guarantee API stability. So the same following the Spark call. And we have this annotation for experimental and developer APIs. But even for those APIs, so if we update those APIs, we will provide migration guide between releases. So, well, the rest of them just new features. We have this sparse data support, also have the decision tree, and we implement distributed matrices with linear algebra operations and principal component analysis, singular value decomposition, and also for optimization algorithms, we implemented LBFGS. So, but for today, I'm going to just talk about sparse data support in MLlib. I want to start it with a story. So basically my major is computational math. And my thesis is about some large-scale sparse linear regression problems. So once I wrote the following sentence in a draft. So I said, I want to really solve large-scale sparse linear list squares. But I sent it to my advisor, and he just struck out the word sparse. Why? So he told me, well, large scale already implied sparse, so you don't have to mention sparse twice. Yeah, so basically, well, if I say everything that is large scale is also sparse, maybe that's a really bold statement. But really, this is true for the world of big data. So sparsity is really almost everywhere. So I can see many sources that can introduce sparsity into your data set. For example, if you want to do feature transformation, and you may want to map numerical features into categorical features, or you may want to map categorical features to numerical ones. And then you do all kinds of transformation, interaction, bucketing. And if you want to process text, you want to work with words and n-grams, backgrams, trigrams, and then they increase the feature dimension by a lot. And also, so for example, for the recommendation, you're working on a huge rating matrix, millions by millions. And then also for other stuff, you can exploit the slow rank structure, right? So essentially, those are all can contribute to sparsity. So for example, I take one example here. I have this one-hot encoding. It's a very standard feature transformation. And you want to map a categorical feature into numerical. For example, we have a feature called country. And we have Germany, Brazil, Argentina. And so one way to map them in is just assign an index, right? So we map Germany to 0 and Brazil to 1. Well, then the question is whether we can use it in a linear method, right? Linear method means linear combination of if this is a single feature, after we train the model, we get a numerical value indicate the coefficient. What does it mean if the coefficient is 0.5, right? So is it, and what's the meaning of 0.5 multiplied by 1 by Brazil or multiplied by 2? So you still need to treat it as a numerical feature. That means it doesn't apply to linear method like logistic regression or linear SVM. So the right way to do that is called this one-hot encoding. Basically, consider that you have 10 categories, and then you map each feature value into a vector of size 10. And only one value is 1, and all the others are zeros. Then Germany becomes 1, 0, 0, 0, and Brazil becomes 0, 1, 0, 0, 0. So in this way, you map a categorical feature into a set of binary features. Then you can use linear method to train this model and get some meaningful result. But look at the data now. So it contains a lot of zeros. The density is the number of non-zero elements divided by the total element is 1 over the number of categories. So it's very sparse if you have many categories. So then the next thing is bucketing. So maybe you want to convert a numerical feature to categorical features. For example, we want to work on the time of the day, and we want to predict some frequency of some activities. And we can use the second of the day. But, well, if I apply a linear method, I assume that it has a linear effect on the value of this feature. But actually, no, right? People has a very high activity, maybe, 9 a.m., or maybe after lunch, 2 p.m. So you really want to just transform them into categorical features, like the hour of the day. You create buckets, right? So map each time, a single time into those buckets, this hour of day, you have 24 buckets. But now after you have done this mapping, and it becomes sparse. And the density is then 1 over the number of buckets now. So this is where sparsity comes from. So also I can show you some real world data sets. The first one is Netflix price. It's close to 500,000 users and 20,000 movies. But the number of observed ratings is just 100 million. So the density is just a little bit over 1%. Also, we have this is a standard training data set called RCV1. And the number of examples is, again, more than 500,000. And number of features is about 50,000. The density is even lower. It's less than 1%. And in this case, you need to really think serious about sparsity, because if you use a dense format to store the training data set, it will be 270 gigs. But if you use a sparse format, well, it's just a 600 megabytes. So I also want to view sparsity in a broader sense. Basically, I want to view the real-world data set as either sparse or low rank and plus noise. So think about it, but maybe you think, I have a really dense data set. It's all images. A dense image, well, it has an array of pixels. And for each pixel, it has 3 colors. And you have a value between 0 and 255. So however, this image looks very dense. However, if you switch to the frequency domain, if you apply some wavelet transform or cosine transforms, you will see the image is really sparse. And many coefficients are very small here. The magnitude of those coefficients, you can simply ignore them because they're just noise. So after you treat them as zeros, the image becomes very sparse. Also, for a huge rating matrix, so for Amazon rating, this is much in a bigger scale than the Netflix rating. It's 6 million by 2 million, 2.5 million. And if you want to make some prediction, do you want to really fill in this matrix? How much storage you need if you want to really want to fill in this matrix? So you don't want to do that because you know, well, people's preference fall into very limited categories, where I always look for some electronics. So other people look for some books, right? So based on those assumptions, and the rating matrix is approximately low rank. So you can just represent the matrix by 2 matrix factors, and then you can reduce the storage, and that's also one kind of sparsity. So, so sparsity is almost everywhere. So as a user, machine learning user, you need to know how to recognize the sparsity in your data. And if you are a developer for MLlib, so you need to think about how to utilize the sparsity if the training data is indeed sparse. I will talk about those two. So in Spark 1.0, and we added sparse data support in all the 3 APIs. And now we take advantage of sparsity in both storage and computation in all the linear methods, naive Bayes, k-means, summary statistics, singular value decomposition. And before 1.0, we also support collaborative filtering is already sparse. The input is already in a sparse format. So before we add sparse data support, we look over the linear Java linear algebra packages that can support sparse linear algebra. And we take a look at those linear algebra packages and then did a benchmark on the operations we need. And we will take a look at those operations, basically how to add a sparse vector to a dense vector. And we did a small benchmark, and we pick Breeze as our underlying implementation. And Matrix Toolkit Java is also very fast, but it has some license issues. We cannot include it in Apache project. So we choose Breeze for this. And the format we use is very simple. Basically, for sparse data, you just store the non-zero elements. And it basically has 3 members in the data structure. One is the size of the vector, and the non-zero indices, and the non-zero values. And remember, the indices are always ordered. So that's the storage format we choose. And there are some alternatives, like you can use a hash map, or you can use compressed storage. Well, those are not very efficient for numerical computation because usually we just need sequential access and in our machine learning algorithms. This is the reason we choose this format. So for user, you only need to know how to create a sparse training data set or how to save and load a sparse data set. So basically, for create a sparse vector, it's almost the same in all 3 language APIs. You just call vectors.sparse, and with the size of the vector, the index array, and the value array. This is same for all 3 APIs. And then if you want to create a labeled point, a training example with a sparse feature vector, just call label point with a label and the feature vector. And then maybe you want to save your training data set for future use. And we support libsvm format. That's very standard for, well, machine learning for classification problems. And you can call this save as libsvm format. You will save the data into libsvm. And we also support, in the coming 1.1 release, we'll have mllibs format. It's something like a JSON typed format, but it stores the information about the vector size. So that's different from the major difference from the libsvm format. It doesn't tell you the the number of features in your data set. So for loading, it's very easy. Just load libsvm file or load label data. That's also available in 1.1. So the next thing I want to focus on how to implement machine learning algorithms that can take advantage of sparsity. Here is basically tell you, well, for most algorithms, the runtime complexity should be proportional to the number of non-zeros in your data. And J means number of non-zeros. So the first example is, I show you, this is example basically from Twitter data. And we have 12 million tweets. And about the feature set, the feature dimension is about 500. And the sparsity, the density is about 10%. So if we store the data set in dense format, it will be about 50 gigs. And if in sparse format, it's just 7 gigs. And the running time also, we receive about 4 times speed up. So it's both storage and runtime performance gain. So how we can achieve that? So for k-means is very standard algorithm. The essential computation is just compute the pairwise distance. To compute the pairwise distance of two vectors, you need to compare, you need to take the difference of individual components and then compute the sum of squares, right? So let's say even here the C vector is the current center, is average over a set of points. Basically, essentially, it will be a dense vector. But the input data point X here will be a sparse vector. So, but if you use this formulation to compute the distance, well, you still need to do a linear time on the feature dimension. It's not take linear time on the number of non-zeros. So, however, if you play with this linear algebra, and then, so the L2 distance can be expressed as the norm square of the sum of norm squares of those two vectors, and minus the inner product of them, 2 times 2. So now the question is, if we can pre-compute, so C is, the number of clusters is small, and we can compute the norm of C. And the norm of X, since X is immutable, X doesn't change, we can pre-compute the norm of X as well. Now it's the thing left is just the inner product here. And take the inner product of a dense vector with a sparse vector, you only need a linear time on the number of non-zeros in the sparse vector. So in this way, we can reduce the total running time from a dense from the linear time on the feature dimension times number of examples to the number of non-zeros. And also Spark give us the advantage of caching those norms in memory. And you don't have to recompute it, and you don't have to alternate the existing data set to store the norms. So it's very efficient. And the next thing is I want to talk about linear methods. So linear method, essential computation is to compute the gradients and compute the sum of them, and then do the updates. So why we call it a linear method, basically the loss function can be expressed as a function of the inner product of X transpose W. X is the current training point, and W is the weight vector, and Y. So since this is, if we can express the loss function in this way, and the gradient can be expressed as f prime times just 2 doubles and times x. So inside the function, we need to compute the inner product. That still, well, it takes just a number of non-zeros And then we do a multiply scale this point by a scalar, and then so it still just takes a time of proportional to the number of non-zeros. So we can simply implement in this way, right? So for all the points, we just for each point we compute its gradient, and then we do a reduce, and then it sum them up and get the sum of gradient. But this is not good because first it creates a lot of small objects. It's temporary object. For example, you compute the gradient, and the gradient will return you a temporary vector. And now you sum up two vectors, and you give you a new vector. It's a new object. And the other problem with this proposal is it will adding up sparse vectors. And that is not efficient because you need to modify the index array and you need to modify the value array to reallocate memory to fit new data. So actually in MLlib, so for each partition, we first generate a dense vector of all zeros. And after we compute the gradient, we do not create a new vector. And we add the gradient directly to the dense vector and then compute the sum. So in this way, we can have very fast random access and also just no temporary object creation. So it will be very efficient here. And then we also have this, can take advantage of sparsity in the summary statistics. Basically, we need to ensure that it's both accurate and fast. Just make the running time depends linearly on the number of non-zeros in your data. So also recently, we have a PR about sparse singular value decomposition. We can do singular value decomposition and using by computing the eigenvalue decomposition of the Gram matrix. So basically, this singular value of A is equals to the square root of this eigenvalue of A transpose A. And we can use Lanczos algorithm to compute the eigenvalue decomposition in an iterative way. So it's very efficient for sparse data. And it only requires a function that can provide you matrix vector multiplication. That's only thing this algorithm needs. So take a look at this operation. So think about A is a tall matrix with many rows and maybe a smaller number of columns. And then we can express this A transpose A. We don't have to compute it. And basically, it's a sum of this inner product times each row of A. So, and remember, the inner product here is also, well, only takes a number of non-zeros time. And then multiplied by A is just a scaling. It's same as a linear method. And then we can compute it really quickly and very efficiently. So the next thing is you need to think about whether your data is dense or sparse, whether I should switch to sparse from dense or whether I should switch to dense from sparse. So first one, think about the storage. For sparse formats, we take about 12 times number of non-zeros plus 4 bytes for the storage. And dense format is just 8 times n bytes. But basically, if the number of non-zeros is less than 2/3 of the total number of elements, then, well, sparse format can take advantage of storage. But if you are thinking about the running time, that would be really problem dependent. Because in sparse format, the linear algebra operation is not as efficient as dense format. So for k-means, maybe, well, you need a density less than 10% to see some certain advantage on the running time. And for linear method, it's not really computation heavy. So then perhaps you need less than 5%, but do play with your data and to see, well, which one is the best for you. So also in MLlib, we'll introduce new algorithms, and then the user will have choice over which algorithm to choose. And now, for example, we have this sparse SVD, and also we have this alternating least squares. Both algorithms provide matrix factorizations. And here, this is an experiment did by Lipu from Twitter. It's on a Twitter data set about The first one is 5 million by 8,000. The second one is 41 million by 42,000. You see, the sparse, the singular value decomposition is much faster than ALS. But you need to understand why it's much faster here. So because we implement this alternating least squares, and such that it's scalable on both directions. So you can have millions by millions rating matrix. But for SVD implementation, we assume that each row can be stored in memory. So it only is scalable on one direction. But if your data fits this really well, just choose SVD. Also, there are some difference in the machine learning models as well. But basically, just try to learn your data and try to how to find the best algorithm that fits your data. So for the implementation of sparse data support, I want to thank the following people. Basically, David Hall is the author of Breeze, and Sam just cleared out the license issue with Netlib Java. Also, the rest of guys implement all those functions. So to summarize, basically, try to view your data as either sparse or low rank plus noise, and to see how it can change your modeling. And then remember that MLlib supports sparse data in almost all its implemented algorithms. And if you want to contribute more algorithms, think about the complexity, how it is associated with number of non-zeros in your data. And if you are a user, just try to understand your data and recognize sparsity. So that's, oh, yeah. Questions?
Yeah, so for a sparse matrix, you store the row vectors or the column vectors?
So we will store the column vectors. That's the basically standard from our traditional Fortran and C libraries.
Yeah, so this is another way people learning party to compress the data. They can build a Huffman tree for this kind of a lot of the zeros, right?
Yeah.
So in your case, it is a very few one, most of them are zero. So I cannot, almost immediately I was thinking, we can just use the Huffman tree to compress the data, so we also have a very good sparse representation, right?
Yeah, but think about the running time on decoding. You need to have a map, right? So then you need to have know how this value map back to the original value, and that's not efficient in computation.
Okay, so that was concealed, but it was not.
Yeah. Also the other thing is the values are double values. It's not integer values. I think it will be hard to do that Huffman encoding.
So what do you think is the most efficient way for storing the map from like raw input to sparse index?
Sorry?
Well, if your raw input is with string keys and values, how would you suggest storing the map from keys to the sparse?
So you can convert. If your input format is something like coordinate format, you have this row index, column index, then value. You can do a group by and order by index and indices, and then create sparse vectors.
But you need to save the object if you're going to be scoring with new data.
Yes. Yes, even with your new data, you should the data should be organized such that each observation is a single record, right? And then you can convert each observation into a sparse feature vector.
Just had a specific question. On one slide you mentioned that the centroids in k-means clustering, they tend to be dense.
Yes. So the centers are computed as the mean of the vectors that's most closest to this center. And think about if you take the mean of many points, and if a single vector contains a non-zero value on this feature index, then, well, it will be non-zero in the final average. So then, well, the cluster center is generally dense. Yeah.
So you mentioned your SVD implementation uses like a level system.
Yeah.
So in Mahout they use like a stochastic SVD.
Yeah, stochastic SVD only guarantee approximation, And the approximation factor is basically k times log k. So it's hard for user to control and what's the accuracy they want. It's also a randomized algorithm. You cannot guarantee that you always get the right factorization. Well, it's a good model, but we want to start from very basic. Yeah, so we provide exact computation of SVD.
Would you get like possibly speed ups if you could implement that?
So for that one, so we really need to create a matrix that can be scalable on both dimensions, and then the SVD really makes sense. Yeah, otherwise it's not that useful, I think. Yeah. No questions? Oh.
Do you also provide some basic operation on matrix, like inverse matrix, or?
Right now, all the linear algebra support on a single machine is provided by Breeze. And Breeze the underlying package is netlib Java, and it's basically a Java wrapper over LAPACK and BLAS. And you can call the netlib Java's implementation of matrix inverse or solve a linear system.
So it only works on single machine, is that?
Yeah. Right now, we don't provide a compute inverse of very big matrices. Okay. Thank you.
Maybe I should. Do you have it on the on your laptop? I don't know how to switch this.
Oh, just switch back to the computer.
I'm sorry.
No, always hit the front. You might just for the screen. Okay.
Hey, Kevin. You know how I get out of the this mode where it's extended?
Just if you could minimize it real quick.
Oh, we didn't get it.
Yeah, you gotta minimize it.
Sure.
So I can access the desktop.
I think it was it. Yeah. It was there for a minute. Great. Looks good.
All right. Just go ahead and bring it up.
Great.
Looks good.
Great. Ready to start. This has been a really great event so far, and I'm excited to be participating in it. Thank you for coming to my talk. My name is Philip Ogren, and I'm going to be talking about, oh goodness, sorry, the title's missing somehow. Technical difficulties, excuse me. Anyways, I will be talking about leveraging UEMA in Spark today. This is not a talk about Oracle strategy. I work for Oracle as a software developer. This is not a talk about Oracle's use of Spark. If you are interested in that, I encourage you to come back in September to Oracle Open World, where my management team will be presenting on a data enrichment cloud service there. This is really just kind of a narrow technical talk of stuff that I'm working on. So UEMA is a Apache project that's been around for a long time. It's very mature. It's been in, as an Apache project for 8 years or so, and was in development for about 5 years before that. It's very it's pretty well established. One of its claims to fame was being the backbone, the framework that was used for all the pre-processing analysis that populated the knowledge base for IBM Watson, which was famous for winning Jeopardy a few years ago on TV. Unstructured information implies lots of possible different input types, audio, video, image data, but for the purposes of what I use it for, I think of it as a text processing platform. Spark, which we all know and love, is a big data platform, but it's not really a text processing platform per se. And this is important to note because lots of our big data applications deal with various kinds of human language text, from customer reviews to Twitter feeds and blog posts. So the goal of this talk is to demonstrate a way to take a UEMA analysis pipeline and call it simply from an RDD full of strings. In this case, an analyze text function could be something like named entity recognition or syntactic analysis. Classified text could be a function that would do perhaps sentiment analysis or sort of basic document classification. So UEMA has been used for all kinds of natural language processing tasks. I list a few of them here just to give you a sense of the kinds of things people do in this community, in the text analysis community. It's been used on a variety of domains and genres. But UEMA is not really a toolkit of a library of these activities. It's really a framework that provides APIs and abstraction layers for really orchestrating different kinds of text, different kinds of text analysis. There has been an ecosystem of toolkits built up around UEMA, and I list a few of those here. I'll call out the first two are Apache projects. OpenNLP has been around for a long time. It's really well suited for a variety of languages on newswire text and kind of general domains. CTakes is another Apache project that provides a number of analysis components suitable for clinical data that you might find in medical records. And this is an incomplete list, of course. UEMA has a lot of features that I'm not going to introduce you to. For someone like me who builds analysis engines, this is what UEMA looks like. On the left, you have a collection reader which serves up documents to a pipeline of analysis engines which work in turn on a document. And then at the end, you spit out some results to a database or a file system. And I'll call out two features of UEMA that really help the orchestration of the analysis. One is the flow controller. This diagram shows what the default flow controller looks like. Run this analysis engine, run this analysis engine, run this one, in sequence. Where a typical analysis engine would be something like a tokenizer and a sentence detector on the front end, followed by increasingly more complex analysis engines. But flow controllers provide for conditional and iterative type flows so that you can have very sophisticated pathways through an analysis. The CAS is the only other acronym I'll use today, but it's kind of central to the power and beauty of UEMA. It stands for the Common Analysis Structure, and I'm going to describe that in detail. So the Common Analysis Structure, the CAS, is this data structure that you get one per document or per unit of work, whatever your unit of work is. And it holds the content and the analysis of the document. The content of the document is seen in something called a view. A view is a really nice abstraction that in many cases you want multiple views because, often your data is in a format, in a specific file format, such as XML or JSON or some kind of arbitrary file format that you're stuck with. And perhaps one of your first analysis engines will be to provide a plain text rendering of that document, and you would put that in another view and have analysis associated with that. In experimental research, it's really nice to have multiple views. If you have a gold standard labeled corpus that you're training on, put all your gold standard labeled data into a gold view, put all your system results in another view so that you can compare the results to give, to produce evaluation metrics. The analysis of a document is represented as typically like annotations. So the kinds of annotations that you'll see are structural things like tokens and sentences and paragraphs, and up to much more complicated structures like syntax and named entities or various semantic entities that you would see in a document. So the way the CAS works is I'm kind of beating on the CAS because it's an important abstraction for sort of cleanly expressing complex analyses on a document. I'll just diverge for a moment. The NLP community has a long and rich history of skunkwork pipeline projects where a Perl module feeds into a C module, all via different file formats. And the CAS is really a nice way to orchestrate different kinds of analysis on the same document at different stages of the analysis. So one of the backbone ideas of the CAS is a type system, which is a very it's a user-defined representation that's quite expressive and flexible. And basically you use it to define the annotations you're gonna perform on the document. So the kinds of types that you would create in a type system are a token, sentence, part of speech tags. If you were, for example, parsing abstracts from scientific literature, you'd have a set of types corresponding to authors and titles and addresses. Each kind of domain or genre is going to have different types that you're going to care about. The CAS also has a very sophisticated indexing schema that allows for API calls like give me a book title that would occur before the author annotation that I have. Or a general pattern that you would see is I've already run a tokenizer in sentence detection. I'd like to loop over every sentence, and for every sentence loop over every token. And then and then do something on each token. So the kinds of things you might do on a token or a document is extract features in a machine learning context. So a lot of the NLP tasks are framed as machine learning tasks, and the CAS basically allows you to write feature extraction libraries that are generic across lots of different type systems, so you don't have to re-implement the same kind of low-level lexical features that you generally feed into machine learning algorithms. I'll also I don't have any data available at the moment, but it's a very efficient, high-performance data structure. So as with many frameworks, the price of admission to abstraction paradise, so to speak, is configuration hell. And UEMA is no exception here. If you'd like to tag some text, so to speak, with your analysis engine, you just have to do these seven simple steps. Wrap your tagger as a UEMA analysis engine in their API. Write an XML descriptor file. Write a CAS consumer. This is an object that takes information out of the CAS and writes it out. Write another descriptor file. Write another descriptor file. Write another descriptor file. And then invoke this thing called the collection processing manager with yet another, I guess it's with the previous descriptor file. To invoke a word used earlier today in a video, if you've done this sort of thing, you feel itchy afterwards. And you're not very close to our goal here of taking an RDD full of strings and just running, analyze this text. So a project that addresses this is called UEMAFit. It's a sub-project within UEMA. If you go to uema.apache.org, there's a link on the left-hand side labeled UEMAFit. And it provides factories for instantiating UEMA components without the descriptor files. It provides injection, which uses Java annotations to remove boilerplate code associated with configuration. The initial use case of this was for unit testing, because who wants to write descriptor files for unit tests or maintain them, which is worse than writing them. So where we want to get to towards kind of a simple invocation of UEMA from Spark is to move away from the sort of batch pipeline approach where you have a collection reader and something on the other end that writes out results, to encapsulating the whole pipeline into a single method call where you have a string going in, and on the other side you have some rich object that describes the analysis that came out of it. And given something like that, you can see pretty simply how we can do a flat map on an RDD of strings. So POJO is for plain old Java object. So basically, we want to shrink wrap the whole thing down into a single method call. And so the technique I've used for that is to have a constructor that creates the analysis engine. This method, create analysis engine, could be arbitrarily long and contain a number of sub-analysis engines within it. So it would describe an entire pipeline. And then from that analysis engine, you can create one of these CAS objects. So you have to do that at initialization. And then when you call the analyze text method, you pass in a string called myText. You reset the CAS. You set the document text of the CAS. You process your document. And then you extract values from the CAS to return to the caller. So there's just kind of one more glitch in this solution, and that is UEMA components are not serializable. Everything in Spark needs to be serializable. I haven't tried cryo on this yet. Perhaps that's a workaround. But what I've been doing is just simply labeling my member variable that's an analysis engine as transient, and then I implement the read object method and call the initialize method there. That's worked just fine. So in my abstract, I promised to provide a complete working example. I've gotten most of the way there, but it's actually not available yet. I will post instructions to the Spark users list when that's available. But what I've provided is, or what I've cobbled together so far is really an example that shows how to invoke OpenNLP. It's a little bit of a silly and contrived example because OpenNLP is perfectly fine to call as a Java library, but they do provide UEMA wrappers. And so basically I'm providing a POJO wrapper around their UEMA wrapper around their POJO library. But it is nice to have kind of all the mechanics in one place to demonstrate the API that's required. And then a simple example that has the Spark of type string that invokes the POJO wrapper. So that's my talk. Yeah, any questions? Sure.
You look to being able to break up a UEMA pipeline into separate Spark components?
Do you have a use case in mind for that? Sorry, the question is, have I looked into breaking up UEMA pipeline for kind of, sorry. Sure. So yeah. So one of the kind of simplifying assumptions of what I've done here is that each thread gets the entire UEMA pipeline And so you're just running it across. I mean, as long as it fits into memory, into each node's memory allocated to it, then it runs really great. You're concerned about a UEMA pipeline that perhaps takes too much resource to do it that way? Sure. Well, so UEMA does provide a mechanism to access external resources, which may be too large to give a single instance of that to every thread that's running. So it would probably make sense to configure this in a way where you would have some of those large external resources available per worker that the different threads would access. That's kind of built into UEMA, so it shouldn't be too hard to make that work across a Spark cluster. Sure.
Any other questions? Thank you very much. Oh, there we go. It has to be connecting this thing that the keyboard gets disabled.
Hello. Hi, everyone. Thank you so much for stopping by and giving me a chance to talk about the work we are doing. It's been a great day so far, and I hope you have also had a lot of fun. Wow, so let me begin my talk. My talk today is titled Fuzzy Matching with Spark, and I'll talk about the problem we are solving, why we are solving, and how we are leveraging Spark for solving this problem. So briefly, something about us. We are a group of people who like to challenge ourselves. We like to set new goals. We like to look at new ways of solving an existing problem. We just like to push ourselves, and that's the reason why we have chosen the problem that we are attacking. So as we all know, like as big data scientists and engineers, data is growing, and data is growing at a phenomenal speed. The various sources of data, the kind of data, the variety of data is making it very difficult to analyze and to make any kind of sense out of this data. Any models, any sophisticated predictive analysis, any kind of statistics you want to do on your underlying data, if your base data is not clean, there is no way you can get correct results for your business. A good size problem, a big problem with the underlying data is duplicate data. So now as data is coming from various sources, or data within the single source will have chances of being duplicated. These duplicates are not exact duplicates. There are duplicates, records are typically multi-attribute, and it's very difficult to spot out exactly which records match with each other and which don't. The problem is also a hard problem to solve, because if you look at n records, you're actually comparing n into n, you basically are comparing n into n pairs, and that makes it quadratic in nature and very difficult to solve. Again, there's no standard notion of similarity across records. So how do I say if the first name has 3 characters same and the last name has 6 characters, probably first 6 characters same, and the age is nearly 4 or 5 years apart, probably these people refer to the same person? Similarly, with organizations, products, restaurants, movies, any kind of data, there is no standard notion by which we can define similarity. Underlying data also has a lot of omissions, typos, errors, and other issues, which makes the problem even more challenging to solve. So my favorite use case here, you have burgers, would you like fries? Cross-selling and upselling. A very standard business problem. You have various services and products which you are offering to customers, and you often want to increase your revenue through cross-selling and upselling different services and products. And you want to make sure that you're not inundating your customer who's already part of a product to try out the same product again. So this is where you're matching data across 2 different source systems and seeing that you're only getting targeted users for your products and services. Lead generation, again, I have a database of organizations who are my vendors or who are my customers, and I source other data from maybe LinkedIn or Crunchbase, or I buy a database of customer or vendor information. Now, how do I mash up this data? Because the formats would be slightly different. There would be typos, there would be null values, and make sure that I'm targeting the right leads. Banking and financial sector, a very big use case in various scenarios. Personal credit ratings, you're getting data from various sources, and you would like to have a consolidated view of this data to be able to ascertain what is the credit history of an individual. Fraud detection, definitely don't want to hand out loans to defaulters, not to deal with people in your blacklist. And a lot of other use cases. Yellow pages, any place where you're consolidating information from various channels, catalogs, inventory, product listings. So you have a problem where, data could be duplicated and there is a need for fuzzy matching. So when we looked at this problem, although the problem is complex, but we wanted to solve it in a very simple manner. We had a wish list of features that we would like to build, and our biggest challenge has been that we want to work with any kind of data. We don't want a tool which is specific to a domain, because this problem has applications across domains. So this was our simple wish list: work with any kind of data, highly scalable. We want to attack the quadratic nature of the problem, and we don't want the user to do any manual configuration of rules or algorithms. Now, when we evaluated Spark, we were very impressed. In fact, we were blown away with the features that it offered. The first thing that stuck to me, I'm sorry, this is not in the order that I wanted to present in, but so the first thing that struck us was that there was no need to orchestrate multiple jobs. Spark was taking care of all our tasks and scheduling them in the appropriate manner. We also do a lot of sampling and create a lot of heuristics about our underlying data so that we can choose the right ways to bring nearly similar records together and only then perform comparisons. So Spark's sampling gives us a great benefit there. MLlib has been a great help. We are completely based on MLlib. We are using some of the existing algorithms which are available in MLlib, on top of which we've also built some of our clustering and classification algorithms. We look at the same record from multiple views, and Spark's nature of keeping data in memory really helps us scale this application, besides the distributed and fault tolerance that Spark provides. So how does a typical refire workflow look like? We have a very simple step. We take labeled data from the user. Every user has a notion of similarity on what records are same or not same according to them, according to their business case, according to their need. And we ask them to label this data. So in this case, if you would see, there are typographical errors. Each field has variations. Some of the fields are probably same, some of them are missing. And the user is the best judge to say, in their scenario, would they like to label this data as same or not? We also accept a set of high-level data definitions from the user, data definitions which are very high-level in terms of, is your data alphanumeric, is your data categorical? So you can specify that at a field level. You run, so basically based on this training data, we create our models on what is the best way to partition this data so that we get similar records together, and then the best algorithms to run over this data so that we can say with confidence which of these are true matches as defined by the user. And once this is done, this is the output where, again, duplicate records are labeled together with the same label in the first column. So if you look at this, again, the tool has gone and looked at various kind of differences across all the fields, and in combination provided what is a duplicate record and what is not a duplicate record. So pretty much that's it. Feel free to visit our website and let me know if you have any interest or a use case for this. Questions? Yes, please.
How do you take the user's input and then turn that into, algorithmic decisions?
Okay. So the question is, how do we take the user's input and turn that into algorithmic decisions? We ask the user to provide us two sets of data. One is labeled positives and one is labeled negatives. So labeled positives are is data where we are saying that these records are actually duplicates. Labeled negatives are records which we are saying these are not duplicates. Then we run our own custom algorithms on top of it and find what are the best algorithms which kind of get all the similar records together. And then we learn the rules and we apply that on the entire set of data to present the results. Yes, please.
So at the heart of this is like an n-squared operation that you simply cannot do because it's infeasible.
That's right.
If you could do that, that would be this naive way to approach it. So can you say anything about how you're breaking it down and avoiding the n-squared problem?
Okay. So once we take the label data, we actually learn what is the best way to partition this data. So we use, based on the input data, we actually we learn the custom partitioning rules and apply that on the entire set of data. So that's how we've broken this. This problem is not just n-squared, this problem is also finding the right way of matching multiple fields. So that is also an area over which we have worked. So this is a two-pronged problem actually. And both are again achieved through a combination of in-house algorithms as well as clustering and classification, which is available in MLlib. Yes, please.
So you probably have like a bunch of complex types in there, like say phone numbers that contain a bunch of formatting. Does your system deal with those on like a case-by-case basis by like learning what formatting to ignore, or do you ways that it's really hard to kind of normalize. So can you speak to that?
Okay, so at a high level, we are actually not doing any normalization of data. What we are expecting is that if we are looking across records, across multiple fields of the records, we are not actually converting, any Robert into Bob, and those kind of normalizations we are not doing. I'm sorry, could you repeat the second part of your question?
Yeah. So, well, I mean, the example of phone numbers is one where you've got like punctuation and things like that that can affect it. So, do you have custom sort of parsing for those sorts of types as well beyond just categorical versus numeric?
We don't have a specific phone type as of now, but it's pretty easy to build something which, given the base framework that we have. So as of now, we have very high-level data types, as in alphanumeric, numeric, categorical, text, which is longer text, or word, which is smaller text. That's it. Any other questions? Thank you so much.